Quiet breathing to heard music. The term quiet breathing has been used to describe or capture all kinds of respiratory behavior that doesn't involve any kind of actual action. So, without vocalization or movement or any influences encouraging a particular pace of breathing. And quiet breathing is thought to consistently involve an active phase in the inspirations that are rather quick and relatively shallow, and an elastic, effortless expiration phase as the body returns to mechanical equilibrium. Quiet breathing statistics, such as the respiratory rate, are routinely used as the baseline reference for all kinds of respiration studies. But these measurements sometimes are taken while participants are given something to look at or listen to, such as an audiobook, and sometimes without any kind of stimulus at all. Music studies have generally assumed that what people are listening to can affect their breathing. Often they will take baseline recordings in silence and then compare the average respiratory rates to the rates measured as people hear this piece of music or that piece of music. And these studies have consistently found changes in respiratory rate to musical stimuli and have tried to correlate them to affective features of music. However, many of these studies are reporting only averages and don't discuss how that respiratory rate change may be taking place, and other explanations for changes in respiratory behavior have not been looked at extensively. Maybe we can find out more about why this is happening by investigating when and how exactly this change is taking place. In a study initially intended to compare micromotions of participants standing quietly while listening to music over headphones and speakers, 28 participants' breathing was recorded with a respiration belt. All participants heard all musical stimuli twice, each over headphones and over speakers, and the previous study found an increased head motion with headphone wearing. The stimuli were 6 45-second sound clips ranging in complexity from a simple digital metronome to excerpts of electronic dance music. They are presented in random order, alternating with 30 seconds of silence. The figure here presents one respiratory sequence measurement along with one listening session presented to participant over headphones. This shows typical variability in respiratory cycle captured with chest stretch measurements, and the large jumps are likely not stimulus related. The respiration sequences were initially recorded at 10 Hz with the sweet spot belt and app. After realignment against the motion capture data and resampling, signals were low-pass filtered, and the inspiration onsets were picked out by function tuned to quiet respiration. This algorithm uses a reliable shape of the active inspiration phase to locate the earliest strong evidence of inspiration based on second-order inflection points and local signal behavior. Expiration onsets were set at the next plausible local maxima. The analysis to follow focuses on breathing statistics related to time, as chest stretch sensors are not very reliable measures for quantities such as respiration depth or flow rate. The first part of the respiration analysis looks for categorical difference in breath statistics under the conditions of sound, whether there's a stimulus playing or whether it was in silence, and the playback, headphones or speakers, followed by an analysis specifically trying to contrast the stimuli. For each 30-second segment of silence, or 45-ish stimulus segment, we calculated the median statistic for breaths during that segment. Here, medians were used because respiration often is disrupted by extreme outliers unrelated to experimental conditions. And these segments also differ in the number of breaths, making the impact of outliers more variable still. The durations calculated were respiratory period, so the entire breath cycle, inspiration duration, and expiration duration, all reported here in seconds. Two-way repeated measures ANOVAs were applied to these median descriptors of respiration during silent and sound segments against the factor of playback. And the playback medium was not found to have a significant effect on any of the breathwise statistics, but sound versus silence was significant. Respiration period medians decreased by nearly half a second on average. The same shape analysis on inspiration durations showed an average decrease of 0.1 seconds, nearly as large an effect as measured on the entire respiratory cycle, despite this being just below the sample period of our chest stretch measurements. And the median expiration phase duration was also significantly decreased between silence and sound intervals. Note that the decrease in expiration phase duration, around 0.36 seconds, is larger than its proportion of the average respiration cycles in silence or in sound. This suggests that the expiration phase is more strongly affected by the presence of sound than inspirations. The stability of the respiratory period has also been a feature of interest when considering breathing during demanding tasks. Augmented breaths and other anomalous cycles are common regardless of context, while creeping changes in arousal are expected to shift the base rate over time. So we chose to quantify median sequential differences in phase duration, the absolute change from one breath to the next. The bottom plot shows how this helps handle the frequent outliers in these sequences. Applying the same two-factor repeated measures and ANOVA analysis to these features found again that playback had no significant effect or interactions, but the presence of sound did produce a significant decrease in variability, even when captured with this very conservative metric. Sequential variability appears to have the strongest change in the inspiration, but this contrast would be good to re-examine with breathing captured at a higher sample rate. After establishing the strong effect of any sound stimulus on respiratory phase durations, we also checked whether there was variation between these stimuli. Again, playback had no measurable effect, but stimuli were found to be a significant factor for the 3 durations tested. However, these differences were not as strong as sound to silence, and only a few pairwise differences were found to be significant after correction for multiple comparisons. These plots report the distribution of relative median durations of phase components across participants. The stimuli are ordered in these graphs roughly by their musical complexity, with metronome, rhythm, and andre being progressively richer in terms of the number of tracks involved, but fairly static over their 45 seconds. And the last 3, Neelix 1, 2, and Pish, have melodic components and formal boundaries more typical of EDM. The pairwise differences were only noticeable between andre and the metronome and andre and Neelix 1, but there's no clear explanation as to what aspects of the stimuli might account for the contrast. The stimuli varied in rhythmic complexity, musicality, beats per minute, but none of these factors correlated with the average relative durations. There was also no significant difference in sequential difference medians between the stimuli. So now let's look more closely at when this respiratory behavior changes. Now, a note as we get into the analysis of these respiratory sequences over time, we are reporting quantified durations from the onset of the intervals over which they are captured. That means that, for example, inspiration duration appears to change with the onset of the breath that is shorter or longer, rather than after the cycle has been completed. The top plot shows the measured breath durations for all listenings to the metronome stimulus, with 20 seconds before the onset of the stimulus and 20 seconds following its end at 47.5 seconds. The second plot shows the ratio of responses that are increasing and decreasing in respiration duration by at least half a second within a sliding 5-second measurement window. Now here we see the majority of responses drop in respiratory period right around the onset of the sound stimulus, peaking at 2 seconds in. This represents changes in a window of 5 seconds that begins before the sound onset. This is not a sign of premonition. Rather, it indicates that participants seem to be shortening the respiratory cycles after the onset of inspiration. The offset of the stimulus also shows a similar peak in period increases, suggesting that listeners' respiratory cycles were affected mid-breath there as well. We can look at this more closely by considering inspiration and expiration phases separately. Inspirations are the active phase of quiet breathing, when muscles are cued to contract and produce a sufficiently deep breath for gas exchange with minimal disruption of everything else. Activity levels here show a pretty steady rate of inspiration duration shifting back and forth during the silence interval, but we catch a concentration of decreases in participants' first breaths after the onset of the metronome stimulus. We've highlighted the signal interval being counted for the activity levels reported in the bottom graph. The expiration phase is passive, elastic, during quiet breathing, so it would be fair to assume that it would change following the shortened inspirations, but that is not the case here. Expirations shift just as quickly, if not faster, than the inspiration phase. The proportion of expirations showing a big decrease begins to grow before the onset of the stimulus. This means that some expirations that were in progress when the metronome started were immediately shortened, advancing the onset of the next breath. Looking at offsets, the story is a bit more complicated. For inspirations, there is a less marked concentration of phase lengthening following the end of the metronome track, though the proportion of decreases does dip somewhat. Expirations, in contrast, show a lot of mid-phase changes to the stimulus audibility shift. Let's look at the respiration phase durations for all the stimulus onsets. In these graphs showing expiration duration shifts of at least 0.3 seconds, most listenings showed a drop of expiration duration around the time that the stimulus started playing, no matter which was sounding. And many of these stimuli seem to provoke changes in expirations beginning before their onset. The stimulus differed slightly in how they began, with full sound clicks for the metronome, to a quiet starting hum in Neelix 2, such as, or fade into a clearly ongoing music in the example of Pish. But change in expiration behavior was consistently measurable in the current or next expiration phase. Looking at the offset of stimuli, expirations were less concentrated in their extensions. But this may be due to the fact that many of these stimuli would fade out, adding some variability to when listeners perceived the sounds ending, like we hear in Andre. The change back to pre-stimulus expiration durations was still accomplished within an average breath duration. So what we've shown here is that respiratory behavior seems to change substantially with the presence of sound stimuli as compared to silence. Inspirations and expirations are reliably shorter and more consistent, and the change in this behavior occurs rapidly with the onset and offset of the sound stimuli. It's fair for us to question whether the effect that has been measured of music on how people breathe is really due to stimulus characteristics or something more fundamental. Given the limitations of these stimuli, there's quite possibly other factors that can come into play, but this is also an opportunity for us to consider an alternative hypothesis: the listener's attention to a sustained, predictable stimulus. The changes in respiratory behavior is consistent with this auditory attention-oriented task. The reduced period and increased regularity facilitates the management of auditory masking to manage the sound of respiration and be able to infer clearly around its imposition on our auditory perception. Faster respiration rates have been associated with increased mental effort, and part of what we are doing when we are listening to musical stimuli is generating expectations, so that change in respiratory behavior may be more compatible with that form of engagement. And action has been found to change respiratory behavior when people engage in mind wandering. Those kinds of imagined things may idiosyncratically express themselves in their respiratory behavior, and that is more likely in silence in this condition than during the relatively short sound stimuli. The results of this analysis do have some implications for music research. For one, we can say very confidently that quiet breathing is different during silence, without stimulus, and during musical sounds. And in that case, perhaps silence is not the best baseline for us to be using when studying people's responses to musical stimuli. A metronome or simple click track would be a better reference. And here we should recognize that arousal may not be the dominant mechanism for respiratory rate change in the context of music listening. Though, of course, stimulus contrasts from other experiments suggest that affect can also be an additional factor. And lastly, there's an opportunity here potentially to be using respiration duration and regularity as some kind of indicator of participant attention, though this hypothesis does warrant further and more direct study. So, a few final takeaways here. One, it might be time for us to recategorize quiet breathing into multiple categories of respiratory behavior. Second, silence may not be the stable baseline suitable for all kinds of experiment paradigms. Also, there may very well be a lot more information about listeners' experiences in the respiration measurements that we've been collecting for ages. Lastly, for my sake, please use sample rates higher than 10 hertz when recording respiration, because then we might capture a lot more interesting detail in the shape of individual breaths. Thank you very much to my collaborators, and thank you for listening.